Hi, everyone. We're happy to have Raghavendra and Addanki presenting at our ANC seminar today. Raghav is currently a PhD student in the theory group at University of Massachusetts Amherst, where he is advised by professors Cameron Musco and Andrew McGregor. He's broadly interested in the design and analysis of algorithms, as well as causal inference and machine learning. And today he'll be talking about approximation algorithms for learning causal graphs. And here's Raghav.
Hi, everyone. Today, I'll be presenting approximation algorithms on learning causal graphs. This is based on joint works with Shivakashi Vishwanathan from Amazon, Andrew McGregor, and Cameron Musco from UMass Amherst. I'll spend first 5 to 10 minutes on topics related to causality. After that, I'll describe a formulation which relates learning the causal graph to a clean theory problem. And then from then on, it will be designing approximation algorithms for this problem. Okay, let's see the motivation for studying this problem. The motivation comes from this fundamental problem in causality called causal discovery, wherein we are given certain random variables in our system. Some of the random variables are called observable variables, where we can measure them. We can look at their values. Some of them are hidden variables, where we cannot measure these random variables. So in this example, measured variables or observable variables could be qualifications prior to college, opportunities after college, average salary after graduation, and college ranking. There could be hidden variables such as college culture, which could influence these observable variables. The goal in causal discovery is to identify all the relations in this graph, even the relation between hidden and observables, along with observable relations. So it's possible that we can recover some parts of it, but in certain settings, we cannot recover all the relationships using just the data we see. That is called observational data. So the goal in this field is to use this observational data and perform certain experiments or interventions, which we'll define shortly, use these interventions or experiments to learn the full causal graph. So let's first look at what a causal graph is. So a causal graph is a directed acyclic graph containing observables V and latent variables L. Edges of the script G, which is the directed acyclic graph, between observable variables, induced on the observable variables, is called the observable graph, denoted by G. You can see that there are no latents in the observable graph. We also make this assumption of semi-Markovian assumption, wherein we assume that every latent exactly affects two observables, and there are no latent edges. This is the causal graph which we are interested in. So how do we identify a causal edge? As I mentioned, one can use the observations on these variables, observable variables, to recover some directions of these edges. But it's possible that we cannot recover any directions. And in that case, we need what are known as interventions. Informally, an intervention is carried out in a control setting where we fix a set of variables to certain values in their domain. And this fixing the set of variables to their values will help us learn all the causal edges. How does it help? We'll describe it, but this is the informal definition of what an intervention looks like. And the structural causal model framework introduced by Pearl, it says that set the variable or a collection of variables or a set of variables to a value in its domain and evaluate the resulting distribution. For example, change the ranking of a college and observe if the opportunities after college for the students are affected. If we do this process of fixing the variables to a value in its domain and evaluating the resulting distribution, we can look at the independence relations in this distribution to identify the causal edges. So that's the popular way of finding causal edges. Sometimes it happens that we can detect the presence of causal edge, but not the direction. So this is not a general setting, but this is a restricted setting where we know that there is an edge between two nodes, but we don't know the direction. Such a graph, which is undirected, is called skeleton graph. The skeleton graph is defined on observable variables. And given a skeleton graph, an intervention on a set of nodes helps us recover the directions of all edges between S and V minus S. In traditional TCS, this can be thought of as a cut oracle. So if you perform an intervention on a bunch of nodes, you can recover all the directions instant on the set S. So intervening on V1 and V4 will let us recover edges V1, V3, V1, V2 in this example. Sorry. Once we intervene on S, how do we recover these directions? For that, we use what is known as a CI oracle, conditional independence oracle, which says given any two variables, we can check if they're independent or not. Is Vi independent of Vj in the interventional distribution S? Such oracles are standard in causality, and we assume this. We also assume that the probability distributions on the variables which we observe on interventions or just on observational data capture the edges of the graphs accurately. Otherwise, we cannot recover the edges. If these distributions are very far off from the graph, we cannot capture them. So these are called faithfulness and Markov conditions. These assumptions are also necessary. Now,
I'm sorry, if you don't mind me asking, can you just say a little bit more about that second assumption?
Yeah. So, sorry, in this faithfulness assumption or Markov assumption, we assume that the dependencies captured in the distribution correspond to an independencies in the graph. So you can take the graph, suppose you have a graph, and there are certain conditions known as deseparation conditions, which will give you whether two nodes are independent or not from the graph structure alone. We need not look at any distribution. Just looking at the graph, we can say if V1 is independent of V2, if they are blocked by a set S, something like that. If we know from the graph that these two are independent, we want that the distribution which we see in the real world also has that in its distribution. We suppose V1 and V2 are independent in G, then we want V1 and V2 to be independent in the distribution as well. This is faithfulness, and the other direction is given the distribution, our graph also reflects it. That is Markov.
So intrinsically, I mean, if your graph is correct, that must be true, right? But so this is sort of an assumption about like there isn't so much noise that you might accidentally think that there's a correlation. Okay.
Yes. These assumptions are so faithfulness assumption is contested in causality community, wherein you say that these distributions capture the graph exactly because of the noise thing you mentioned, and there has been some work trying to address this assumption, like moving away from faithfulness. So yes, so in that way, using these interventions and combined with these independence, we can recover the edges. Now, intervening on a set of variables could be different for a different set of variables. Like if you intervene on one variable, it could have a different cost associated with it. Whereas if you intervene on another variable, it could have a different cost. So we capture this in what is called linear cost model, where suppose G is an undirected graph, a skeleton graph, as I described previously, without any directions given to us. In this linear cost model, we assume that every variable has a cost C of Vi associated with it. And intervening on any set of variables is simply the sum of these costs of variables present in this set. For example, this captures the setting where interventions on variables are different. So intervening on college ranking might be easier than intervening on opportunities after college. So if you create an intervention on two of these random variables, we should somehow account for these costs. We cannot have intervening on a bunch of variables to have the same cost as intervening on another bunch of variables. So linear model captures this. There could be other cost models as well, but none of them have been looked at, and this is a very open area in that setting. So formally, problem of learning G can be posed as follows. Given a skeleton graph, the undirected graph, which I described, a budget on the number of interventions, we can only do like 10 interventions, say, and the cost of interventions, cost function on every variable. We want to recover the directions using these M interventions that minimizes the cost, sum total of each intervention on every set. We also define an epsilon approximately learning objective, where we want to recover the directions of all but epsilon n squared edges of G. So we might miss out on epsilon n squared edges of G, and we are okay with that. So let's look at some prior work before we go into our results. We can recover the graph scale. So the prior work can be broadly categorized into two areas, basically. One where there are no hidden variables, there are no lanes in the system. In this case, we can recover the graph skeleton, which I mentioned, using just the observational data. Once we recover the graph skeleton, in Aberhead et al. And Shanmugam et al., they give necessary and sufficient criteria for interventions required for recovering the directions. So you use observational data to get the skeleton, you use these necessary and sufficient criteria to get back your graph G. So it's very well understood in that setting. And in a linear cost model using these relations, they get a true approximation very recently by Lindgren et al. But the setting of latence is not at all, well, it's severely lacking in understanding. So first of all, we do not know how to even obtain this undirected graph or the skeleton graph. Even if we allow for experiments, even if we allow for interventions, we do not know how to recover this undirected graph. And there is no optimal notion also here known. If we are given the skeleton graph, there is no known algorithms that obtain non-trivial guarantees for recovering the directions. So this is supposed by some oracle which tells you that, okay, these are the causal relationships, but we do not know its directions. Even if we know that, even if we know the skeleton graph, we do not know good algorithms in this. In a recent work, we also give a true approximation to recover ancestral graph that captures path relations. In some sense, path relations are easier to recover than the original graph G, and we show that we can give true approximation in this. Here are our results. I won't be presenting all the results, so that's why I've just selected some subset which I'll be presenting. For the problem of recovering the directions of the graph G, we show that if the graph is arbitrary, we can obtain a 2 log n approximation, and this is tight. We also present a conditional hardness showing that there is no approximation algorithm which can obtain better than log n. To move beyond this, to get constant factor approximations over here, we go into the bi-criteria goal where we are happy with recovering all except for epsilon n squared edges. So in that setting, we give a 2 approximation while losing out on epsilon n squared edges. There could be other approximation notions. This is one notion which we defined. And defining an approximation notion for learning G is also widely open. No one has defined it before. Okay. So now, having said this, we'll connect to some structures which are very useful and which have connections to graph coloring and all. So let's look at the set of interventions which we perform on this graph. Let them be denoted by S1 to Sm. If you look at these interventions and write them in a matrix form, so such that the kth column of this matrix is the set Sk. So S1 denotes the characteristic vector of the first column denotes the characteristic vector of S1. Similarly, the second column denotes the characteristic vector associated with S2, so on and so forth. So in this example, suppose if S1 contains V2 and V4, we set the row corresponding to V2 to 1, V4 to 1, so on and so forth. So this matrix can be filled out when we give S1 to Sm. So the reason why we shift to matrix view is, so far we have looked at this set of interventions which must be performed. Now we'll look at the row format and make use of these row formats in an interesting way. So instead of picking interventions and finding them one by one, we'll look at a node and see its contribution to all the interventions simultaneously. So L of I denotes the ith row corresponding to the node Vi. So it's a vector associated with every node. L of 1 represents vector with V1, vector of V1 in this matrix L, so on and so forth. So we say that this matrix associated with a set of interventions S1 to Sn is a separating matrix if and only if this Li is not equal to Lj for all edges Ei and for all edges Vi, Vj, and E. So if two nodes are joined by an edge, the row vectors Li and Lj should be different. That if that is true, then it's called a separating matrix. If this property is satisfied for all but epsilon n squared edges, then we call this an epsilon separating matrix. As you might have guessed, the separating matrix is essentially equivalent to graph coloring. Let's look at this matrix and view each row as a label for the node. So for vector V1, the row vector associated with V1 could be thought of as a label for V1. For node V2, the row vector associated could be thought of as a label for V2, so on and so forth. Because two nodes which are connected by an edge will never share the same vector, they'll, in some sense, they are not color. This is a proper coloring of the graph. So given separating matrix, we can obtain a proper coloring and vice versa. So given the skeleton graph G, and S, if S denotes the set of interventions, L its corresponding matrix used in recovering E, we show that the matrix L associated with the intervention sets should be a separating matrix. This is a necessary and sufficient criteria we give. I'll not go over the proof of this, but after we make this assumption, we can formulate our problem of learning G into a clean theory problem as follows. We want to output, we call this the min cost SS problem. We want to output S1 to Sn, these are M sets, such that the sum cost of these sets is minimized, and the corresponding matrix L is a separating matrix. Because if it is a separating matrix, we know that we can recover the graph. We can rewrite this objective in terms of the matrix as follows. Instead of summing up over the sets and nodes in the set, we can just sum up over the nodes in the graph and multiply it with the number of times this node is part of the sets. So the multiplicity of this node in S1 to Sn, which is essentially equivalent to the number of ones in the node vector corresponding to node V. So which we call as the weight. So the objective now is iterate over all the nodes, multiply it with the number of ones or the number of times it is part of in these sets, and combine all of them to finally get our objective. This can be thought of as a weighted graph coloring problem as well, where the weights come from this matrix L. An approximation goal here would be to output a good separating matrix L, which is within alpha times the cost obtained by L star, the minimum cost separating matrix. A bi-criterion goal would be to obtain to return an epsilon separating matrix, which is alpha optimal. If you have any questions, please ask me. Otherwise, I'll describe how do we find this good separating matrices. Okay. How do we find a good separating matrix? First of all, this problem is known to be NP-hard even for interval graphs. When G is caudal, there is an algorithm that achieves 2 approximation factor. For an arbitrary graph G, we do not know any hardness result. So we first show that this problem is hard, meaning you cannot get any approximation better than log n. It's based on the following conjecture, which has been looked at in fairly recent work as well, but it's not widely known, which says that if you know that your graph is 3-colorable, you cannot use sub-polynomially many colors and color your graph. So for a fixed constant gamma, there is no polynomial time algorithm for coloring a promised instance of a 3-colorable graph using n to the gamma colors. So the reason for this conjecture is we know that it's NP hard to approximate chromatic number to within any polynomial factor for small gamma. Even when the graph is known to be 3-colorable, even when chi of g is 3, the hardness known is still constant. You can't do constant. You cannot color it in polynomial time using constantly many colors. When chi of g is 3, current best known algorithm uses n to the 0.277 colors. As you can see, there is a huge difference between the current known hardness and the best known algorithm until now. So because of this, we formulate this conjecture where we assume that any 3-colorable graph cannot be colored in sub-polynomially many colors. Assuming the above conjecture, we show that there is no polynomial time algorithm for finding an little of log n optimal separating matrix. Recall that separating matrix just says if you take the matrix and view it in the row form, 2 nodes which are connected by an edge have distinct row vectors. I'll briefly describe the sketch for this proof. The reason it's pretty simple. So let's consider a 3-colorable graph with unit costs. So the cost of every node is 1. Let L be an output of our algorithm A of G, that is alpha optimal. We prove by contradiction, so we assume that alpha is little of log n. Using this algorithm A of G, we give a new coloring of graph with n to the little of 1 colors, which will violate our conjecture, which said that you cannot color it using sub-polynomially many colors. So how do we do that? First, observe some structure with respect to the optimal L star. Because your graph is known to be 3-colorable, let's look at these 3 color classes corresponding to, the nodes. So this is the first color class, this is the second color class, and third color class. Each of these nodes in each color class could be assigned the same weight vector, same vector. Because they don't have an edge between them, you could assign same vector to them. Therefore, the separating matrix with lowest cost will do that. And if you look at the matrix, it'll just have 3 distinct row vectors spread out over all the nodes. Because we assume that m is more than 2 log n, and this could be more than 3, you could assign the first class with weight 0, the second class with weight 1, the third class with weight 1 once again. If you do this, you have a matrix L star with weight at most 1 for every node in this graph. L star will do even better, so this is a valid argument. Now, let's look at the cost associated with our algorithm. Because all of them are unit cost nodes, you can write it as sum of these weights associated with every node. Because we know that this is alpha optimal, we can bound it by alpha times the cost of optimal separating matrix. We've argued just now that the weight of every node is at most 1 in L star. So this can be bounded by alpha n. So the cost of our algorithm is at most alpha times n. So let's look at L. In this L, using a simple averaging argument, it is easy to see that there can be at most n by 4 nodes with weight more than 4 alpha. If the number of nodes is, if there are more number of nodes, then the sum of these would exceed alpha n. So there are at most n by 4 nodes with weight more than 4 alpha. You could pick your favorite constant over here, and it would be like n by 2 with weight more than 2 alpha, something like that. Now, we will show how do we color the graph using this. Let's look at L. And we know that there are just n by 4 nodes with weight more than 4 alpha. Among the remaining 3n by 4 nodes with weight at most 4 alpha, let's look at these nodes in L and look at how many distinct row vectors are there in these. For every distinct row vector in L on these set of nodes, you create a new color. Once you have created these new colors, you assign this color to the node corresponding to its vector. Because this L is a valid separating matrix, this is a valid coloring of G. In all, you have only used the total number of colors used is equal to the total number of distinct row vectors in this matrix L. The total number of distinct row vectors is simply upper bounded by the binomial coefficients from 0 to 4 alpha. So you could have at most m choose 1 weight 1 vectors, m choose 2 weight 2 vectors, so on and so forth. So the total number of colors we've used is, if you do the calculation, you'll get that it is little n to the little of 1. Once we have that, we run our algorithm on, we throw away all the 3n/4 edges, 3n/4 nodes, because we have colored them. Now look at n/4 nodes with high weights, run our algorithm on that. We recurse on that. In each iteration, we are peeling away more than n/2 nodes. In log n iterations will terminate, and we would have obtained a new coloring using n to the little of 1 colors, which will refute the conjecture. So this, in this way, we can argue that there's no little of log n approximation for this problem. Now we'll show a very simple 2 log n optimal algorithm, essentially saying that this is tight up to constant factors. It's based on the following intuition. I wouldn't go into proof for this, but it's based on the following intuition. Basically, nodes with high cost should be assigned the 0 vector. Like when you assign these vectors to these nodes, you want to assign nodes with high cost the 0 vectors, so that the total cost contribution of them in your optimal and in your algorithm is essentially 0. If you do not assign that, your approximation ratio would be arbitrarily bad. However, ideally, we would like to use a maximum independence set in this case to find the nodes with high cost and assign it 0 weight vector. But finding it and approximating it is very well known to be hard. We look at the vertex cover of graph and look at its complement. We can observe that if X is vertex cover, V minus X is an independent set. And we'll use this as a proxy for maximum independent set. There's no relation between vertex cover and maximum independent set as such. It doesn't give a good approximations, but for our purposes, it is sufficient. For finding the vertex cover, we use the standard 2 approximation algorithm. And for the nodes which we identify as part of vertex cover, we just assign them log n weight vectors. We don't care about edges of the graph. We just assign them because we assume that m is more than 2 log n, so we have enough vectors to assign. And for the v minus x, where x is the vertex cover, the 2 approximate vertex cover, we assign it the 0 weight vector. This simple algorithm of using the vertex cover and assigning the weights obtains 2 log n approximation. So far we have seen that this problem is log n hard. It has a hardness of order of log n, and then we have seen a simple algorithm that obtains this factor. Now, how do we get constant factor here? For that, we'll have to relax our goal, and we'll look at epsilon approximately learning a graph. By this, I mean we are interested in learning all edges except for epsilon n squared many edges. In terms of separating matrix, this corresponds to looking at the matrix and the property that Li is not equal to Lj for every edge is only violated for epsilon n squared edges. Those are the matrices now we are interested in. For this, we'll look at the greedy strategy introduced in 2018 by Lindgren et al., where it's once again based on the intuition we have seen so far, which is you find the maximum cost independent set in the graph. You assign all the nodes in S, the lowest weight vector available to you. So you start out with 0 weight vector, you assign it to the maximum independent set, you remove these nodes. The In the next iteration, you assign weight 1 vector, you remove these nodes, and so on and so forth. Because you will be assigning m, choose 0, m, choose 1, so on, and that many vectors continuously. And you'll be done when the graph is empty. Because we are assigning same vector to every node in an independent set, it's a separating matrix. This greedy algorithm is known to be too optimal if we can find MIS in polynomial time, the maximum cost independence. As I said before, finding this MIS or approximating it to within any polynomial factor is also NP hard. For this, we use the idea of near MIS to overcome this limitation of finding MIS. A near MIS could be thought of as a set of nodes with cost as high as maximum cost independent set, while only containing epsilon n squared edges. It's a very sparse graph with cost as high as maximum independent set. So in the left-hand side, V1, V2, V3, V4 represents MIS with cost C of S. On the right side, we have a graph with few edges with cost at least as high as C of S. And yeah, but it is a sparse graph. It contains few edges. This will be sufficient for our epsilon approximately learning G because of our relaxation. So how do we find these sparse graphs with cost as high as MIS? For this, we use connections to property testing, wherein we give an algorithm, a polynomial time algorithm for testing whether an independent set with cost rho times C of V exists or not, where rho is some constant 0 to 1. If so, we return a set of nodes that contains at most epsilon n squared edges with cost at least rho times C of V. So we can use this subroutine to find the maximum cost independent set. And if we find one, we'll return a set of nodes with cost at most epsilon n squared in polynomial time. Here, I'll describe the intuition for how we do this. Let S, this is our graph. On the left side, you have the entire graph, and S denotes an independent set of size rho times n. And we are interested in finding this independent set of the graph. Because we are interested in efficient algorithms, we can't enumerate overall possibilities or all possible subsets. What we do is we use sampling to identify this S. How we do it is as follows. We first identify a sample of size t selected uniformly at random with repetition. With replacement. So we pick t many nodes from this graph uniformly at random. After obtaining this t many nodes, we look at a subset of these nodes of size rho t by 2. Using Chernoff, you can see that the number of nodes present in this S in the sample would be roughly expectation would be around rho t, and we can argue that there is a subset of size rho t by 2 in our sample. Because we do not know which of the subsets is fully contained in S, we iterate over all possible subsets of our sample V tilde and pick one and process it. So the final goal is to obtain a set U which is fully contained in S. So essentially, we're looking for a small subset of S. And once we have this subset, we'll expand it into S. So we sample it, we look at subset of this sample, and in one of the subsets, we'll hit a proper subset of S. Once we hit this proper subset, in this example, V1, V5, and V7, we'll expand it into S and recover all the nodes of S. That's the intuition. To make this a bit more concrete, let me describe what tau of u means. Tau of u is just the set of neighbors of u in the graph. Tau of capital U is the set of neighbors in the union of all the nodes in U. And tau bar of u represents the set of nodes with no edges to any node of u. So basically, in this example, S is V1 to V7, U is a strict subset V1, V5, V7, as I described previously. tau bar of u will include S as well as this node V8, because V8 has no edges to V1, V5, and V7. That's the definition of tau bar. There are no edges to any node of U. So if U is a strict subset of S, we can observe easily that S will be contained in tau bar of S, which will be contained in tau bar of U. So if V belongs to S, it will not have any, because V is part of an independent set, it will not have any edges to S. So V will also belong to tau bar of S. Now, if we pick some V in tau bar of S, because it doesn't have any edges to S, it will not have any edges to U, so it will belong to tau bar of U. In some sense, using this small set U, we were able to obtain a larger set tau bar of U, which encapsulates this S. Now, all we need to do is pick a subset of this tau bar of U. First, we found a subset of S, then we expanded it into tau bar of U. Now we want to get back S. What they proposed in GGR 98 was just take this tau bar of U, look at the induced subgraph on this tau bar of U, and pick the nodes with the lowest degree. Just pick mod S many nodes with the lowest degree in this induced subgraph. They've argued that this is a good, this will find you the near MIS. But in our setting, every node has a different cost associated with it. And sampling over here is non-trivial. And it is especially challenging if S is a high cost MIS. And if it doesn't contain a large number of nodes, then we would have to sample a lot of nodes to even hit one of the nodes in this S. So that would make our running time exponential and it would defeat the purpose. So is there a way to sample it better than what these people, what this algorithm which I described does? So that brings us to this notion of a rho gamma epsilon independent set, which will be helpful. Okay, a rho gamma epsilon independent set is defined as follows. Suppose you have this is once again very much related to the near MIS, which we discussed previously. Suppose S is an independent set with cost at least rho times C of V. Then a rho gamma independent set is a set of nodes with cost at least rho into 1 minus gamma times cost while containing epsilon n squared many edges. So we just lose out on this rho gamma factor from the independent set rho times C of V. So our final algorithm would look somewhat like this. You find the near MIS in your graph. For that, you use a guessing strategy. You guess what this rho would be for a maximum cost independent set. Once you guess this rho, you set this gamma and epsilon prime parameters to account for union bounding and approximation ratios. Basically, you find this rho gamma epsilon prime independent sets iteratively until you hit the correct guess rho for the maximum cost independent set. This will give you the near MIS. Once you have the near MIS, you can do the greedy strategy of coloring it with lowest weight vector and peeling off that nodes from the graph. You do this process continuously and you have colored the entire graph and you have formed a separating matrix or you have colored the entire graph. How do we find this rho gamma epsilon independent set? As I described, the issue arises from sampling, and if the set of nodes which are of high cost are very few, like we can't sample them exactly, so how do we do it efficiently? For this, we use the strategy of partitioning the set of nodes based on their costs. So you look at each node and assign it to a partition among V1 to Vk based on the cost. So V1 will contain all nodes with weight with cost between 1 to 1 plus gamma. V2 will contain 1 plus gamma to 1 plus gamma squared, so on and so forth. That's how you can construct these partitions. The total number of partitions will be log W, the maximum cost node, by gamma, which can be treated as constant. So we have essentially formed k partitions of the graph, and k is a constant. And in each partition, we sample set of t nodes with replacement. Once we sample these t nodes, we use the previous intuition where we look at a subset of size gamma rho t by 2 in this partition, and we iterate over this partition. And we iterate over these subsets, and in one of the subsets, we would be fully contained in S. This is not exactly true. You have to pay attention to what partitions you're looking at. I'll come back to this a bit later, but for now, you can assume that all partitions are treated equally, and you can do this. Once you have picked subsets from each partition among the sample set of nodes, we once again we construct this. This is our S, and from each partition we have picked these red nodes. From these red nodes, we construct the tau bar of U, which is all nodes which are not adjacent to these red nodes. This tau bar of U will be fully contained in S. If script U is a subset of S, then tau bar of U will be a superset of tau bar of S. And our goal once again would be to recover S from this tau bar of U, as I described previously. However, there is the important thing to note is we are not running the previous algorithm on each partition separately. If we run the previous algorithm on each partition separately and look at all the nodes together and output them, the number of edges in our graph could be much bigger than epsilon n squared. So you have to look at all the partitions simultaneously, and that's why the tau bar of U is calculated over all partitions and not in each partition. After that, we look at so we have now a subgraph which is sparse to some extent, and we have to pick the nodes which will give us the required cost. So we can't just pick nodes which are lowest degree in this tau bar of U, because that would once again it might result in us picking low cost nodes with low degrees. It will not result. It will not help us get the rho times C of V we are aiming for. So what we do is we look at each partition separately and pick the lowest degree nodes in each partition until the sum total degree is epsilon n squared by k among this tau bar of U. Once we have these nodes, we combine all of them and we output them. So yeah, so it differs in, as I described, it differs in two ways. One is we have to look at all partitions simultaneously. After looking at all partitions simultaneously, we have to look at individual partition to account for the cost. We can show that this obtains a good, this will recover the rho times C of V if one exists. I'll briefly present this proof sketch. This should be simple. What I want to argue is you need not look at all partitions of the graph. You only need to look at what we call good partitions of this graph. A good partition can be thought of as a partition which contains a large number of nodes from S. So if your S contains, if your S intersection, your partition is at least rho gamma times mod Vi, that partition is good. If we just focus on these good partitions, it'll be helpful in extracting the total cost. The reason is just consider the cost present in these good partitions. We can argue that this is at least rho times 1 minus 2 gamma of cost of V. Because the number of partitions we assumed are constant, we can guess which partition is good, which is bad, and based on that, we can just focus on the good partition. Using a similar argument as we made before, we can show that the script U will be fully contained in S and will only contain good partitions. As we have processed each good partition and include the low degree nodes, we made sure that the cost contribution of a particular partition is accounted for accurately. I think I'm running low on time, so I'll skip the proof of epsilon n squared edges, that we recover only epsilon n squared edges. So here's our main result. We show that after obtaining our algorithm, where we use near MISs instead of MISs, we can extend the analysis of caudal graphs to any arbitrary graph and obtain a 2 approximation for this. And our running time is order of n squared in the adjacency matrix model, assuming maximum cost of a node, epsilon, delta are constants. Yes, that's it. Recall that this is, we are learning epsilon approximations for the graph. We are losing out on epsilon n squared edges. So in this talk, we have showed that there is an equivalence between learning a causal graph and finding a good separating matrix. After describing this equivalence, we argued that 2 log n approximation is essentially tight, showing a hardness of approximation. After that, we show that if our objective is epsilon approximately learning the graph, we can get a 2 approximation using this idea of peeling near MISs from the graph. There are also several interesting connections if we are interested in path relations in G. Path relations are somewhat easier to obtain than the actual edge relations in G. And for that, we need to extend the notion of separating matrix to strongly separating matrix, which is essentially equivalent to finding anti-chains if you're familiar with those objects in discrete mathematics. So using that connection, we give several approximations with low factors in 2 of our works. That's all. We'll end with some open questions. So far in the beginning of the talk, I mentioned that we assume that the skeleton graph is given to us. But in causality, that's a very strong assumption. So how do we overcome this assumption is a wide open problem in this. And finding an optimal characterizations for obtaining this would be an interesting direction. Another interesting problem is, can we obtain similar guarantees for sparse graphs? So in this talk, I described algorithms which lose out on epsilon n squared edges, but it is possible that we can obtain algorithms which could lose out on epsilon mod e many edges. That is also an interesting case. We showed that if the graph is hyperfinite and degree bounded, then we can get a sparse guarantee. But for general graphs, it is open and it looks like there should be some hardness result, but we are not very sure about that. And another interesting open question could be improve the approximation factor to less than 2. That's it. If you have any questions, please ask.